like to welcome. Okay, that's Zoom. So I'd like to welcome all of you to this event that is held by the Number Theory Unit at CAMS. You know, the Number Theory Unit has been recently established to host activities about number theory and related topics. And it is our pleasure today to have Professor Ghaith Hiary from Ohio State University. Professor Hiary is an associate professor at Ohio State University. He got his PhD from University of Minnesota in 2008 and held postdoc positions and visiting professor at University of Bristol, University of Waterloo, and IAS at Princeton. He's going to be talking about the Riemann Zeta functions, theorems and conjectures, and computations. It is our pleasure to have him here. He's been a very active member with us in the unit and is helping a lot in many things. We're really very happy to have him here in Lebanon for the mini course over 3 days. But before Professor Hiary starts his talk, I would like to leave the floor for the director of the CAMS, Professor Jihad Puma, who's gonna be talking a little bit about this. Thank you. Thank you, Isa.
So it's really, again, our pleasure to have you all with us for this very, very special event, which in many ways continues on the fantastic effort that my colleagues with the number theory unit at CAMS, Professor Kamal Maqdisi, who is with us in the audience, and yes, and our dear colleague Wissam Raji, who has been also pushing forth on number theory now collectively for more than a couple of decades, with a strong presence at AUB through the mathematics department, you know, a stream of interested and gifted students who are pursuing graduate and postgraduate study in the field, and hopefully contributing to the celebration of the beauty of this field and the queen of mathematics for many. Here at AUB and certainly through CAMS. This occasion is, of course, an extremely relevant one for us in terms of its richness, applications, and accessibility to people from all walks of life, practically, difficulties notwithstanding. So I've watched high school students get immersed in computational number theory over the years, and I believe it's truly an incredible way to access wondrous things about mathematics. And it's a pleasure to have Ghaith, an expert in the field, with us, an associate of the unit, a very active one, with beginning around this workshop and many things to follow in the future. So thank you all for joining us. Thank you, Wissam, for helping make this happen. And thank you, Ghaith, for leading on this effort for us. Thank you.
Okay, can you hear me okay? Yeah. All right, so thank you very much to the organizers, to Wissam, to Jihad, to Kamal, and for all their work to promote number theory and mathematics in the region. AUB is really one of the most active as far as number theory in like this kind of in the area here. I'm originally from Jordan, so very close where I come from to Lebanon. Right. So my goal here is to tell a story that hopefully will make it interesting to make do computations with the primes and the zeta function, and even more general L functions. So maybe some history would be useful. And, you know, I try, because there is a lot of diversity or variety in the students or the participants in the course, ranging from, you know, beginning undergraduate to advanced graduate, mathematics, non-mathematics. I try to put something for everyone, every participant. I don't know if I've really succeeded, but this is at least my goal, okay? Right, so, okay, this one. disconnected. This thing is frozen. Right. Prime number. Oh. Okay. So the prime numbers are the building blocks of arithmetic multiplicatively, right? They are fascinating objects because they're very elementary and there are many easy to state problems about them that are extremely hard, right? Some not being resolved until the last few decades and many more that are still unresolved. One thing that happened recently is that there are more computers, there's more access to computational power. And because of the elementary nature of the primes, you can, with very little background, do numerical investigations about them and learn about them and make conjectures, hopefully ones not found before, right? So this access to computing power made it more interesting to investigate the primes numerically because you could reach scales that were not available before. Right. So, even thousands of years ago, we knew that there are infinitely many primes. This is Euclid's proof of the infinitude of prime numbers, but that's not telling much, right? I mean, just like there are infinitely many primes, there are infinitely many cubes. 1 cubed, 2 cubed, 3 cubed, and so on. There are also infinitely many even integers. But there's a big difference between the density of cubes, how many cubes are there near x, and the density of even integers, how many even integers are there near x. So the question is, how does the density of primes, compare to these kinds of sequences? So it's probably somewhere in between these two densities. Okay. Right. So this line of reasoning was considered by Euler even back in the 18th century. So he was asking basically how many primes are there below a given number x. So here is okay. So here's a table that he made. He did the paper and pencil calculations. He didn't have computers. Tabulating the primes, up to a given n, he calls n instead of x, and n is going in powers of 2, right? And the first column, right, is the one where he's counting the primes. Actually, he's counting 1 as a prime number, which people don't do anymore. So, for example, when n is 2, he's saying there are 2 primes, 1 and 2, right? But nowadays, 1 is not considered a prime number, so the number of primes less than or equal to 2 would be 1, not 2. But, the main observation he made was that the law of primes is that as x, or what he calls n here, increases, the primes become less dense, less frequent. That was the main observation. He didn't quantify this quite, but he did observe that if you looked locally in like small blocks of length 100, when n or x is large, that the number of primes in such small blocks varies a lot. Sometimes the block has no primes, sometimes it has 17 or 18, right? So he didn't understand really why should that variation be happening. And that's what he was investigating basically numerically here. Right. So Euler was attempting to approximate the prime counting function, which in standard notation is called pi of x. This is counting the number of primes p. P is common notation for primes less than or equal to x, right? And he didn't come up with a formula or an approximation for pi of x, but he did the data for it. The first attempt to approximate or give a formula for pi of x was by Legendre. He gave this formula. He said, or he stated, pi of x is approximately x over log of x minus b, where b is this really strange looking constant, right? And he found this b using prime tables that he computed and others have computed up to x is equal to 1,000,000. So he went far beyond what Euler did. The highest Euler reached was around 100,000. Right? But contemporaries of Legendre, like Gauss, Chebyshev, doubted that this constant has significance or is mathematically fundamental. Still, even though such big names doubted the formula, based purely on that numerical evidence, how accurate the formula was up to 1 million, it was recognized widely for many decades. So there was like some power in numerical support for formula like this. And not only this, Legendre used his formula to evaluate sums and products over the prime numbers to give numerical values for them, right? And these were infinite sums, so and were not really evaluated before. Okay, any questions? Right. Okay, now the Legendre formula was supported up to 1 million, but eventually it becomes much less accurate, right? The orange curve here is the Legendre formula. The blue curve is the, let's see, is the approximation by the logarithmic integral, which was favored by Gauss and by Dirichlet. So if you look at this picture, the region that Legendre investigated was up to here, right? And up to here, the orange curve is fluctuating kind of, up and down, above and below zero. So it looked like a good approximation, but had he gone a little bit farther, then he would have seen that the orange curve becomes very large. The error becomes very large, right? So the orange curve is the error in the Legendre approximation, and by the time you get up to 10 million, the error is very large. There's also error in the logarithmic integral approximation, but I'll come back to this, right? The logarithmic integral is this integral here, right? 1 over log of t. And if you want a simple formula or like metric for the size, it's about, if you integrate up to x, you get size about x over log of x. And we now know that the logarithmic integral is the true leading term in the approximation for pi of x. Okay, so I didn't know whether I should be doing this or not, but I thought maybe I could pose a question. If you look at this graph, do you notice a couple of odd things about it? Anything strange? Yes? Right here, yeah. Right, so there comes a point where the error in logarithmic integral and the Legendre formula are about the same, but then they diverge, right? That's one observation. Anything else?
Like towards the end,
Right.
the orange graph increases, the blue graph also increases.
Right, exactly. And that's actually because the Legendre approximation, if you expand it like you did here, then Legendre approximation matches this main term, but they disagree on the second term, right? Anything else? Right, yes, exactly. It's very strange that the error, say in the logarithmic integral and also in the Legendre formula, always seems positive. Always seems positive. I mean, there's, is there a reason why the error should be, given that we know that the logarithmic integral is the true approximation as a leading term for pi of x, why should the error in that be always positive? That's exactly the observation. And this phenomena is called arithmetic bias. It's one of the first examples of an arithmetic bias. Right. So what happened with Legendre is that he had access to a finite set of data up to 1 million, and then he had this parameter b in his formula, and he calibrated b so that the error in his formula is as small as possible up to 1 million. So his formula was accurate by design. He chose b to make the formula accurate, but then beyond 1 million, it actually was bad. Right, and in comparison, the logarithmic integral does not have any parameters that you can calibrate. It's just you integrate up to x, that's it, and you get a number. Right? And another thing is the arithmetic bias phenomena, that the logarithmic integral seems to have always a positive error. So it seemed like, is that really the right answer? you'd expect the right answer to have a leading term that fluctuates above and below zero. Sometimes there is positive, sometimes negative, but this one had always positive. So that kind of confused mathematicians even further, kind of set them astray for a while, for several decades, right? It wasn't until Riemann's 1859 paper that it was understood that the logarithmic integral is the true leading term to approximate pi of x, but the calibration happens not through some parameter b, like Legendre did, but through some or some sequence of secondary terms, which was unknown. And this sequence is determined by the complex zeros of the zeta function, which I'll define and introduce little by little, right? And this was an application of complex analysis and contour integration. So it was an exciting application connecting the discrete to the continuous, the discrete primes to the continuous integration methods. Right. Okay. Right. So let's go over Riemann formula. The form of the formula is that it has a leading term given by the logarithmic integral, and then it has secondary terms given by the complex zeros of zeta, which are denoted by rho. This is the notation for them. Now, to state the formula, some arithmetic functions, lambda and mu, have to be defined, but I will do this later. Let me just write out the formula for now. Right, so Riemann considered, instead of pi of x, he considered this function, f of x. You don't need to worry about the prime in the sum here. This is just technical detail, right? The issue is that f of x, once, you'll see this once I define the lambda function, it's counting not only primes, but also prime powers, like not only the p's, but p squared, p cubed, and so on. So it's overcounting. It's like larger than pi of x. But you can use a method called Möbius inversion to recover pi of x exactly from f of x. And this is this formula here, right? And so Riemann's formula, the formula he derived was actually for f of x, and it's this one here. So a couple of quick notes. The mean term is Li of x, but with a big L. This is pretty much the same as the Li of x with a small l, except you integrate starting at 0, right? But it's pretty much the same. And here are the secondary terms that are over the rows, which are the complex zeros of zeta. These terms here are small and less, they're very easy to understand and less important. And so this was Riemann's formula. Right? And this connection between the primes and the rows was very, very fruitful. For example, Euler's original question about how many primes are there below x, this was answered using the complex zeros, or they're called the non-trivial zeros of the Riemann zeta function. And the first proof of the prime number theorem, which is this statement here, that the number of primes up to x is approximately or is asymptotically x over log of x. This was proved by proving certain properties of the complex zeros of zeta. And to just show computationally how accurate this is, here is the blue curve is the error in the logarithmic integral approximation, which is large and positive. And the orange curve is the error in the Riemann formula using only 2 zeros. I'm not using, it'll turn out there are infinitely many of them, but just using 2 zeros, we have an error that's behaving in an intuitive way, right? It's fluctuating above and below 0, smaller in size, and giving reasonable results. So the arithmetic bias phenomena is disappeared once you incorporated the non-trivial zeros. Right? Any questions? Right, so I'll send a copy of the slides to everyone. I have a list of participants. So if you want to experiment with this, here is a Mathematica code. If you have access to that, to compute this graph here, or the orange curve in this graph. So you can experiment with Riemann's formula and the Riemann approximation for pi of x. Yes. So I'm going to define them. I'm kind of like motivating them. So the non-trivial zeros at the end, they will be zeros of the Riemann zeta function that we know very little about, in contrast to the trivial zeros of zeta, which we understand in full. But I will go over this just in a couple of slides, right? I just wanted to start with Riemann's formula to kind of see how these zeros are like came up. Right. Right. So, okay. So to define the non-trivial zeros, I'm going to start with not the Riemann zeta function, but with the Euler zeta function. These are the same, except Euler considered zeta as a function of a real variable x. And so this would be given by this kind of sum. And the main contribution, well, he had many contributions, but as far as the Riemann's work is concerned, the main contribution is this identity here. So on the left-hand side, you have a sum over the integers. And on the right-hand side, you have an infinite product that ranges over P. And P here is running through all primes, 2, 3, 5, 7, and so on. And the importance of this identity is that it connects two expressions, one where you have the primes appearing and another where you don't have the primes appearing, right? And this infinite product here is called the Euler product. Euler discovered it. He discovered that identity, right? And this is really proved using, you know, apart from some technical analysis stuff, it's proved using the fundamental theorem of arithmetic, that a given positive integer has a unique factorization up to reordering in terms of primes and prime powers. It's just an analytic way to state that here. Right. So you can plot Euler zeta function. Here, Euler really rigorously could handle the region when x is greater than 1, because in that region, this series converges, right? But when x is smaller than 1, this does not. Still, Euler found a definition or meaning for zeta when x is smaller than 1. He did this in a non-rigorous way, so I'm not going to discuss this. But if you plot zeta on for x, here's what it looks like, right? You notice that at 1, when x is 1, there is a pole. X tends to infinity by comparison with the harmonic series, for example, right? So this is the kind of picture Euler was dealing with. You know, even just considering zeta as a function of a real variable x, you can see its importance. It can generate some important arithmetic functions, like the mu function and the lambda function that came up in Riemann's formula. So here's the mu function. It comes up as a coefficient of n to the x in this infinite sum. And this sum is equal to 1 over zeta x when x is greater than 1, or at least. And this one comes when you look at the logarithmic derivative of zeta, which is zeta prime over zeta. You get this function. This one is called the von Mangold function. So we have two functions, mu and a von Mangold function, Merbius function and the von Mangold function. And you can deduce from the Euler product that they satisfy these definitions. So mu is essentially telling you something about does the given integer have an even number of distinct prime factors or an odd number of distinct prime factors, which is this quantity here. And the von Mangold is just counting primes or like detecting primes and prime powers with a certain weight. The weight is given by log of p, where p is the prime or prime power possibly that we're looking at. Okay, so you can generate these arithmetic functions using zeta by looking at the reciprocal of zeta or by looking at the logarithmic derivative, right? And to study such arithmetic functions, you can look at the analytic properties of its of the generating function. And when you do this, you usually go beyond real variables. You use complex variables, which is exactly what Riemann did. He was studying zeta as a function of a complex variable. Typically, this is denoted by sigma plus it, and sigma and t are real numbers. And in this case, you get the same definition. Let me go back, as we have here, except you replace the x with an s, right? And you consider s as a complex variable, right? And then you can prove like some things are not hard to prove, like that this infinite series of zeta, the sum over the integers, which is usually called the Dirichlet series, converges when the real part of S, sigma, is greater than 1, right? You can prove that the Euler product is convergent for sigma is greater than 1. And because of this, we know that zeta has no zeros in the whole complex plane and the whole half plane where sigma is greater than 1, right? So for any complex number S with real part sigma greater than 1, in that for such S, zeta has no zeros. It cannot be equal to 0. This is because the Euler product is convergent. You can also extend the definition of zeta beyond sigma greater than 1, all the way down to sigma greater than 0. So in a larger half plane. And this can be done using this simple formula, right? One thing you can deduce from this formula is because the right-hand side here is an alternating series that, and when S is a real number, that zeta has no zeros on the positive real axis, because this sum would be strictly positive. So zeta cannot be 0. So it's not 0 when sigma is greater than 1, and has no real zeros when sigma is greater on the real line when sigma is greater than 0. Okay. So here's the picture Riemann, or like not Riemann, but like this would be a representation of like a zeta in the complex plane. It's a more complicated picture than what Euler had. And here for, to visualize, I'm plotting 1 over the absolute value of zeta. Taking the absolute value is because I want to get a surface. Otherwise, I cannot really visualize. And taking 1 over zeta is because I want to make explicit the zeros, any places where zeta is equal to 0, because when I take 1 over zeta, I get these zeros become poles, become infinite. So you can see the zeros more clearly. That's why I'm representing it this way. It's a more complicated picture. Right. Okay, so what are the properties of zeta? The basic result is we have something called a functional equation. So to state the functional equation in a more symmetric form, you can define this function called C of S. It's essentially zeta together with gamma. This is the gamma function, which on the real line, you might recognize as the factorial function, right? Together with some other factors. And with this definition, this C function satisfies this functional equation. C of S is equal to C of 1 minus S. Right? And using this functional equation, and moreover, actually, C is an entire function. So it has no poles. Right? And you can deduce from this functional equation and the observations about the zero-free lines and regions that we talked about, this one and this one, that a couple of things, that the only real zeros of zeta are at the negative even integers. This is because you need a 0 of zeta to cancel poles of the gamma function that appear here. And these need to be canceled because C is entire. Right? So we can deduce that. And these are the only real zeros of zeta, and they're called the trivial zeros. Okay? And the second deduction is that any complex zeros of zeta, they're called non-trivial zeros, must be in a vertical strip where sigma is between 0 and 1. Okay. So this notation here means this is the set of all complex numbers S, where S is equal to sigma plus IT, and such that sigma is between 0 and 1. And T can be minus infinity to infinity. So it's an infinite vertical strip where any complex zeros of zeta have to lie. And we know that this strip does not contain any real zeros because of 1 here. Okay, so at this point, I've defined the non-trivial and trivial zeros. Any questions? The second consequence is because zeta, okay, so the first thing is that gamma has no zeros at all. The gamma function just has poles. So the zeros of the zeta function are the same as the zeros of the C function. Apart, you notice that there is an S and S minus 1 here. This S has 0 at S is equal to 0, but this is canceled by a pole of gamma. And the S minus 1 has a 0 at S is equal to 1, but this is canceled by a pole of zeta. So all the other zeros of the C, or the zeros must be the same as the zeros of zeta, right? But we know that zeta has no zeros when sigma is greater than 1. Therefore, by the functional equation, by this relation, C has no zeros when sigma is greater than 1, and therefore by the functional equation, C has no zeros when sigma is less than 0. Therefore, between 0 and 1, there have to be the complex zeros. Yeah, so I'm going to come to the symmetry. I'm kind of building up to this, but yeah, you're kind of ahead a little bit of the. Okay, any other questions? Yeah, okay. Right, so here's the picture we are developing. By the way, this strip here is called the critical strip between 0 and 1, right? And also the symmetry, we have this symmetry relation, and this comes from the reflection principle in complex analysis. And this symmetry tells you that the non-trivial zeros, which are denoted by rho, must be symmetric about the real axis. If rho is a 0, then rho conjugate must be a 0. So they're symmetric about the real axis, right? And also by the functional equation, the rho's must be symmetric about the line sigma is equal to 1/2, which is called the critical line. So we have these two symmetries, and this is the picture we have developed so far. The shape, I mean, it's not a good picture, but at least it shows what's going on. So the gray area is the critical strip. The dashed line is the critical line. This dot here is the pole of zeta at 1. The green dot is the first trivial zero of zeta at S is equal to -2. And the red dots are non-trivial zeros of zeta. They are symmetric about the real axis. They are also by design here symmetric about the critical line because they are on the critical line. Though, as far as we know, they could be off the critical line, in which case they have to be placed symmetrically about it, right? Okay, at this point, maybe just I can ask, pose another question. Why must there be infinitely many rows? Right, and this is a tough question, so I have to provide like a reasonable hint. So the hint is in this formula. Imagine what would happen if there were only finitely many rows. What would go wrong? Finitely, not quite finitely many primes. There could still be infinitely many because, right, Lie of x grows like x over log of x, so it could still go to infinity. It's a difficult question, but yeah. So if there were finitely many rows here, then this side, the right side, will be a continuous function in x. Because every term is continuous, and a finite sum of continuous functions must be continuous. But the left side is not continuous. It has discontinuities, when x is equal to a prime or a prime power. So just because of this, there have to be infinitely many rows. Right? Okay, so we know that there are infinitely many rows from Riemann's formula. Right? And Riemann went further and conjectured, like in the picture I had, that all the rows are on the critical line. So they are as symmetric as can be with regard to that critical line. Right? And one consequence of the Riemann hypothesis, and given Riemann's formula and how the rows connect to the primes and to pi of x, the statement of the RH, the Riemann hypothesis, is pretty much saying that the primes are distributed among the integers as random as can be. That there are no, just like they're placed really quite randomly. And quantitatively, you could state this because the Riemann hypothesis, the RH, is equivalent to the assertion that the error pi of x minus Li of x is the logarithmic integral, is bounded by x to the 1/2 plus epsilon for any positive epsilon. So the error around x is about square root of x. An easy way to understand this is that this is saying that the mean term on its own, Li of x, would capture about half the leading digits of pi of x. So imagine pi of x is a huge number, then about half of the leading digits would be given correctly just simply by calculating Li of x, the logarithmic integral. Right? But we are very far from knowing anything close to the Riemann hypothesis. Pretty much all we know is that there are no zeros on the line sigma is equal to 1 or very close to it. And by the functional equation, therefore, we know there are no zeros on the line sigma is equal to 0 or very close to it. Okay. And even this very modest zero-free region for zeta was the main step to prove the prime number theorem, which took several decades. So to kind of, we shouldn't be probably jumping to conclusions that should be easy to prove bigger zeros of free region. Even that modest one was a huge result in number theory. It's the prime number theorem. Yes. Yeah, so I'm gonna like, that's a whole discussion. So probably could we wait until we get to that part, because yeah. Right. There's another consequence of the functional equation, which is that function we define C of S must be real on the critical line. If you apply the functional equation with S is equal to 1/2 plus IT, you notice that C of 1/2 plus IT is equal to the conjugate of C of 1/2 plus IT. So C on the critical line must be a real valued function. So if you want to find rows, at least simple zeros of zeta on the critical line, you can look for sign changes of C, because it's a real function. So if you find a sign change, there has to be a 0 in between. Right, so how can we compute that C function? Well, you could use that alternating series formula that goes all the way down to sigma greater than 0, but that converges very slowly. For example, if I use 1,000 terms, to compute 1/2 at 1/2 plus 10,000 I, the error is huge, like about 1/2, like 0.46. So it doesn't matter, but in principle, we could do this, okay? I'm not suggesting you should do it, it's not a good way, but in principle, we can do that. We can compute the C function on the critical line. Right, there's another problem with the C function, which is that it decays very fast. And that's because as part of the definition of the C function, you had a gamma factor. And this gamma function is like a very fundamental function. As you go up in the complex plane, parallel to the imaginary axis, gamma decays in size very fast. So that makes it hard. That makes it like hard to compute C when T is large, because you need a lot of accuracy to resolve zeros or to compute C with enough precision. Okay, there are better ways of computing zeta on the critical line, but whichever way you use, you can locate the first few of them. To present the data about them or the list of them, let's number them. By this symmetry about the real line, we can look at the rows in the upper half plane, right, with positive imaginary part because they're symmetric about the real line. So there's no need to look at the ones in the lower half plane, right? And so we can number the rows in the upper half plane, say row 1, row 2, by multiplicity, so that the numbering, that they have increasing imaginary parts. And all the rows that have been computed so far are simple and are on the critical line, so they can be written in this form. The 1/2 is because they're on the critical line, and gamma n is positive because we're looking at the upper half plane. Right? Okay. So, we'll come in a future lecture back to how to compute zeta, but here's the list of the first few gammas, right? So this is up to gamma 11. I'm giving the numbers up to 6 digits, and you can imagine that each displayed entry here is saying that there's a sign change of the C function in an interval like this around gamma j. Right, so this is how we know that gamma 1 is like, so no, sorry, like this gamma 1 entry is saying that there's a sign change of C at this number plus minus 10 to the minus 6. We know more, but I mean, that's enough for me now. Right, and these gammas, these are called the heights of the rows. In general, if you write a row as beta plus I gamma, so you allow for the possibility that the Riemann hypothesis is not true. Sorry. So you allow for the possibility that the Riemann hypothesis, beta could be different from 1/2. If you write each row this way, then the absolute value of the gamma is called the height, and gamma itself is called the ordinate overall. Okay. So these are the ordinates, and these are the heights. And the Riemann hypothesis, using this notation, would say beta is always equal to 1/2. Right? Okay, so we want to understand the distribution of the rows, right? These are the mysterious sequence of numbers that appear in Riemann's formula for approximating pi of x. And one very useful thing to do to understand them is to look at something called the Hadamard product of C. And because C is an entire function, it has this Hadamard product. It's an infinite product, which is taken over all the rows, which are the non-trivial zeros of zeta. And in this Hadamard product, beside the rows, there are 2 constants, A and B. The A is not very important, but if you want to evaluate it, it's given by this relation, so it's like log of 1/2. Okay, the B is more interesting. B is given by an infinite sum over the rows. It's the -1, the sum of 1 over row, and you can get an exact value for it. Exactly, it's equal to this, and approximately this is equal to minus 0.02309, right? And here you have to be careful because this sum is actually divergent. It's only conditionally convergent. So when you do the summation, you have to take a row with row conjugate, kind of pair them together to get convergence. Okay, so here's a possible mini project, and you have enough at this point to actually do this, which is to use numerical computation to prove that gamma 1, that number I displayed in a previous slide, is indeed the ordinate of the first non-trivial zeta 0, and that gamma 1 is a simple 0. So all I said in that slide is that we detected sign changes between gamma 1 up to gamma 11, but I didn't say that there are no other sign changes of C that were left undetected below gamma 1. So I want to prove that gamma 1 is indeed the first 0 of zeta. There are no other sign changes below that, or there are no other even multiple zeros of any type below that. Okay, so we want to verify the Riemann hypothesis in this range for t between 0 and gamma 1. Right, and so here's what you can use to finish this. from the previous slide, we know that there are at least 10 small intervals between 0 and 50, where the C function is known to change sign. That's how we detected these gammas in that previous slide. And these intervals are of length 2 times 10 to the minus 6, right? Because I gave each one to within plus minus 10 to the minus 6, right? And the other thing you know is that there's this constant P that is equal to this infinite sum, which if you pair the rho with rho conjugate is given by this, where rho is equal to beta plus I gamma. And you know that this sum is equal to minus 0.02309. Okay, so if you combine these two things, you should be able to prove that gamma 1 is the ordinate of the first 0, and that the Riemann hypothesis is true up to that time. And that's work with my master student is like to actually take this much farther, you know, to general L functions, not only to zeta. Okay, right. So, okay. So in summary, I hope I made it clear that the rows, in a way, generate the primes, because the prime counting function pi of x consists of this very clear term, which is the logarithmic integral, plus these secondary terms over the rows, and all the mystery and the oddities of the primes come from the rows. So they're, in a sense, generating the primes. Right, so they are important for this reason. They are important for other reasons also, but in this context, at least for this reason. Right, and they immediately, you know, if you understand them, you understand many things about the primes, like the prime number theorem, like arithmetic bias phenomena, and many other puzzling behaviors of the primes. Basically reduced to understanding the distribution of the rows, and like even, you know, the most basic question about them, like that the Riemann hypothesis is true, right, is difficult. Right, and to show, like emphasize how the rows generate the primes, here's another formula that does this in a very non-technical, easy way. I like this formula a lot. It's due to Landau. It says that if you take a number x greater than 1, then if you sum x to the row, for the rows with imaginary part or with ordinate gamma between 0 and t, then if you take enough of those terms in the sum, the value is given by the von Mangold function. This is just this function here is the same as the von Mangold function when x is an integer, and when x is not integer, it's equal to 0. Okay, so just like I'm extending the definition of the von Mangold function to the all x greater than 1, just simply by setting it to be 0 when x is not an integer. Right, and the interesting thing about this formula is that you can write the left-hand side in this form here. Right, so y would be log of x, so x to the row would be e to the row log of x by exponentiating and taking the logarithm. And then you have y1/2. This is the 1/2 here is from the Riemann hypothesis, right? Because if you imagine the Riemann hypothesis is true, so all the zeros will have real part equal to 1/2. And then you have this sum here. And this sum looks like a Fourier transform, right? So what the Landau formula is saying is that the Fourier transform of the 0 ordinates, gamma, at least assuming the Riemann hypothesis, have frequencies given by the primes and prime powers, or given by the von Mangold function. Right, and you can see this numerically very clearly. Here is what the picture looks like. This is the absolute value of that sum I was talking about. This is what's plotted here. And you notice that this sum, and I'm using the first 100,000 zeta zeros, this sum is always equal to 0, then up to 2. There's a prime, it jumps. And it jumps by height log of 2, which is the value of the von Mangold function at 2. Then it goes back to 0. At 3, it jumps by log of 3. Again, the value of the von Mangold function. At 4, it jumps by log of 2 because 4 is a prime power. And in between, it's 0. Right? So you have two discrete set of sequences. One of them is the primes, and the other is the zeros, and their Fourier transforms of each other. At least if you assume the Riemann hypothesis, you can interpret it this way. Okay, so the final thing is that to really understand go deeper to understand the zeros, you want to look at something called the zeros counting function, which is n of t. This is going to be counting the non-trivial zeros in the critical strip below height t, so between 0 and t, right? And this has a simple expression. If you really want to get into it, these are the exact expressions that appear in the formula for n of t, where n of t is the zeros counting function. Theta of t is, so you have basically two terms, a theta of t and an s of t. Theta of t is very easy. It's approximately like t over 2 times log of t over 2 pi e. And very accurately, you can get very accurate values for it. There's nothing unknown about it. S of t, on the other hand, is very much less understood, very poorly understood. All we know is that S of t is bounded by log of t up to high t, but at the same time, we know that S of t is of crucial importance in understanding the rows, the non-trivial zeros. Actually, if you plot, and here's a plot of that, this is, I'm not sure, at a very large height, I guess 10 to the 31. You have two curves here, the blue curve and the red curve. The blue curve is basically a real version of zeta on the critical line, and the red one is S of t. And what S of t does is that it's kind of decays to neutralize the growth in theta of t. And then at zeros, it jumps by 1 or by more if there are multiple zeros, right? So here you have a jump. Like, maybe I should point. You have a jump here because there's a 0 here. You have a jump here because and so on. So S of t is actually contains all the information about the zeros of zeta. Okay. Okay. So given its importance, I have to mention a couple of results that are technical, but they are the basis for important methods for verifying the Riemann hypothesis, basically the Turing-Graham-Russell method. The first result is that S of t, we already know it's bounded by log of t, but we don't know that actually can take on arbitrarily large values. So this is something that was proved by Selberg. He proved that S of t is unbounded, both positive and negative values. So it can be arbitrarily large and positive and arbitrarily large and negative. And also Littlewood proved that if you integrate S of t between up to height big T, then this is the value you get. So if you view this as an average of S of t, saying that the average of S of t is very tiny. There's a lot of cancellation. It's kind of S of t is just up and down, but above and below 0, so it cancels a lot. So if you integrate it, you get some very small values, right? And they are mentioning this because of methods for RH, and that's it. Thank you.
Any questions for our speaker? Any questions?
Yeah, it's very hard. You can reason it out using the stuff I presented so far. You can reason out the arithmetic bias phenomenon. To actually prove something about it, you actually need to define it rigorously. All I said is that the arithmetic bias is like positive, but what does that mean exactly? So you have to define this, and once you define this, you can think about proving something rigorous about it. But you can see why it should happen from the formula I wrote, the Riemann formula. Right?
Beta wasn't about how would that affect the theta function?
So the most immediate consequence of this is that the error term in the prime counting function pi of x could get large. So pi wouldn't, so Lie of x might capture less than half the leading digits of pi of x, depending on how egregious the beta is far from 1/2.
Do you know how to deal with seeing if there's any questions from our Zoom attendees?
I think there's a chat.
Chat.
Yeah, but I'm
If
not
any
sure.
of our attendees on Zoom would have any questions, please type it in the chat.
Yes.
So we know there are no zeros on the Riemann 61. Are there any results? 1 minus x?
No, that would be huge. Not even that. Yeah. All we know is that there is a very small zero-free region just to the left of 1, but the width of that region tends to 0 as you go up. So it's getting like closer and closer to 1. It's like a the width of that region is becoming 0 as you go up. Yeah.
But you know, there are infinitely many zeros. This is a result of that. There are infinitely many zeros on the line 1.
Yeah, we know that. We know that there are, so we know that there's a certain percentage of the zeros they must be on the 1/2 line. Oh. Okay, so distributed as random as can be. So I think this was a statement about the primes, that the Riemann hypothesis is saying that the primes would be distributed as random as can be. Basically, this statement comes from something called the Cremier model for the primes. So the Cremier model for the primes is a probabilistic model where you model the primes by random Bernoulli variables, where the probability that a Bernoulli variable is 1 is, as given by the prime number theorem. Then under this probabilistic version of the primes, you can prove the prime number theorem, right? So basically, if you prove the RH, then you prove that Cremier's prediction holds. So the primes are behaving as randomly as in the Cremier model. That's what's
Vladimir, the lecture will be posted on YouTube. So eventually we're going to post this 3 lectures on YouTube, okay? And we'll send a link to all participants. Okay, any more questions? Okay, thank you guys. See you tomorrow at 4. Okay, thank you.